Hello, and welcome to the webinar Addressing Data Challenges for Cryo-Electron Microscopy. My name is Corey Zarnick. I'm the Imaging Product Manager here at Gatan, and I have the pleasure of introducing Charlie Bowman, who is a bioinformatics specialist at the Scripps Research Institute. Charlie has degrees in microbiology and information science, and is currently working on data analytics for electron microscopy using statistics and machine learning, as well as developing infrastructure, both design and implementation for integrated structural and computational biology, focusing on cryo-electron microscopy suite. Charlie's going to be stepping through a presentation for the majority of this. I'm joined also by George Vasek, who is from DDN. He'll be speaking at the conclusion of this. And I just have a couple slides to sort of introduce things here as we get going. The total number of atomic resolution structures submitted to the Protein Data Bank is growing significantly with respect to the electron microscopy. We see rapidly growing adoption with a variety of instruments, not just Gatan's instruments, but a lot of these direct detection systems are really contributing to the rapid growth of this as we get very small structures in very fine resolutions. Looking at the Gatan specific cameras, most of you may be familiar with the K2 camera. It's been released for something on the order of 5 years. We are now releasing a K3 camera, and just to put things in perspective, I wanted to make sure people were calibrated both in terms of the frame rate and in terms of the data volumes that are coming out. So the original K2 camera was roughly 4K by 4K, 400 frames a second. We've basically quadrupled the speed and increased the area, so you get a larger field of view with a single image. And this translates, is fed forward into the processor where we do the counting and we accumulate frames, which is then passed on to the CPU. And so even though the camera is processing many terabytes of data, what you output is actually a fraction of that, because we take the analog out of the sensor, we digitize it, we count it, we accumulate frames, and at the end of the day, what you get might go from 7 full frames at K2, might be 25 frames. You can do super resolution, you can do anti-alias binning, several different options. I'm not going to go through all the options today, since the point of the webinar is really to focus on the information processing as Charlie's going to take you through. But this is just to sort of put things in perspective in terms of the volume of data, the speed of data, and how things are handled differently between K2 and K3. So, without any further, submit questions. Please feel free to submit questions through the questions pane. We will be monitoring that in real time, and we will take questions at the end. If we don't address your question in person on this call, we will do so in a follow-up, either email or call. So feel free to get started questioning whenever. And I guess I will turn it over to Charlie at this point to begin the presentation.
Thanks, Corey, for the introduction and for giving me a chance to speak. As Corey said, my name's Charlie Bowman. I am a Bioinformatics Analyst in the Ward Group at TSRI, where I work with Andrew to keep our cryo-EM facility running and have a few other things going on. I'm here to talk to you about data challenges for cryo-electron microscopy. I'm going to provide some benchmarks and some advice based on the success of our facility here. A little background about us. At the Scripps Research Institute in Torrey Pines, across from the ocean, underground in a bunker, is the Ward Lab. We're part of the TSRI's Department of Integrated Structural and Computational Biology. We have a state-of-the-art cryo-EM suite underground here. We have 6 microscopes running as close to 24/7 as we can get them, including a Talos Arctica and a Titan Krios, both running K2 Summit detectors. What this allows us to do is have a high throughput cryo-EM pipeline for atomic resolution structures. The Krios and Arctica are running almost constantly, outputting frames and structural data that stream onto our infrastructure and enable us to get atomic resolution information within 3 to 5 days with modern software. Everything from full structures of particles to small molecules and other targets of interest. These past 2 slides should really key you into one of the big themes of cryo-EM right now, is that these kind of structures do not come without significant infrastructure and overhead. For collection, you've got to have a microscope and some kind of detector. Storage, you need somewhere to put all these images, all these frame stacks, all this information. And you need a processing architecture to run these high demand programs that give us the high resolution information that we all want to see. So without further ado, the goals of this presentation are to first understand the importance of computational infrastructure supporting your electron microscopes, and also to provide some data collection benchmarks or reference from an established microscope facility. We get asked this a lot by partners and other people who are setting up facilities, and I think it's great that we're going to have this as a resource to show for the future. The first thing to talk about today is data collection and transfer. Just getting the scope and the detector is only the beginning. You can plug them in, and you can have them running full tilt, but if you don't know where to put your data or how to process it, you're going to run into some problems. Start by saying, what have you gotten yourselves into? Right? The K2 Summit and the K3 are both amazing machines that put out a fire hose worth of data, right? Corey's slides earlier highlighted the differences between the K2 and K3. I'm going to speak to them more here. But the raw output, if we talk about frames and frame sizes of these detectors, is amazing. The K2 is capable of saturating a petabyte in 25 hours, and the K3 is capable of saturating a petabyte in 4.5 hours. This is just raw data output. As Corey said earlier, things are processed and managed into smaller sizes. I like to think about this, though, that if we were talking, say, that these images were still film, and we took the 1500 frame per second statistic from the K3, we could summit Mount Everest in 6.5 hours. Or you could just store it in about a 7-inch drive enclosure. So I'll let you guys decide there. But you know, in the end, this 1500 frames per second is mitigated by a lot of factors: the processor speed, your stage movement, settling time, downtime of the microscope, and then your user limitations such as experience, sample quality, and time constraints. So, you know, the final frame rates that come out of the scope or the camera are well within manageable realms. A couple more statistic slides about the K2 versus K3, just for longevity purposes. If we're looking at the per data set cost, right, so 250,000 particles, you don't really need more space looking at K2 versus K3. The images, while larger and potentially having more frame depth, still show this, you know, they still have particle density in them that you would have in the other images. So technically you need less images to get more particles, that kind of thing. One of the more notable things that Corey showed but didn't really focus on is that the K3 introduces the ability to do your frame flattening in real time, which can really cut down on your data cost overall on your cluster, as long as you don't feel like you have the need to realign your frames later. Now, another big difference between the K2 and K3 is the speed, obviously, right? We saw huge increases in frame rate. This slide here just really shows that, I should say that Latitude is Gatan's solution for automated collection here. And we're comparing the rates of collection to current generation plus collection software, so a K2 in cryo-EM, a K2 in Legion, and a K2 in Latitude, to K3, the next generation camera. You're really going to be able to take a lot more exposures with this camera. It's a very fast camera. And not only that, but the infrastructure with it, the processor and the software are a little faster. And also, the images are larger, right? The field of view of the K2 versus the K3 is about almost, I think it's about 40% increase. So while you're taking frames a lot faster, you also don't need to take as many to get to your particle counts that you need to, which allows you to really increase the throughput, which is why the K2 puts out such a much higher raw number. And Gatan here is saying that adding the K3, you can actually almost double your throughput. So that's quite impressive. But where do we put all that? How do we handle all this new data streaming off of these K3s in real time? Terabytes and terabytes per day. The first place to think about how to handle this is with your data collection, right? I already showed examples of serial-EM and Legion and Latitude, right? How are you going to handle your collection? We have to start with the basics. Do you have a separate collection PC that coordinates with the microscope and camera a la Legion, or are you using EPU or Latitude or serial-EM and running everything on either the microscope computer or the camera control computer? This is important because you need to make sure that the connections between these computers are very strong and that they're reliable and have maximum uptime, right? Before we start even to talk about storage or processing nodes, the most important part of any cryo-EM facility is a strong network backbone, because if your computers that are controlling the microscopes cannot talk to one another, they cannot send commands to the microscopes. And if the computers can't send the information downstream, they're inevitably going to fill up, overload, and stop collecting, and that's going to result in downtime for you. So this is the first real thing when you're thinking about setting up a facility that you need to think about. You need to talk to your IT and get this in place. One of the major sources of fluctuations in collection, so downtimes, stoppages, delays, that we noticed, or I noticed a few years ago when I started working at Scripps, was in this connection downstream from your collection computers to your cluster. You could have many different cluster configurations, many different network configurations between your collection computers and your cluster. But if this stops or is slowed down, your collection will also stop or slow down. To mitigate this problem, one of the first real big recommendations that I bring out is the buffer system, right? And some of the companies that make these hardware, like Gatan and FEI, are starting to implement things like this. But essentially, a buffer system is just a medium spec server, a frame buffer that sits between your facility and your centralized compute. And what it does is provide a small reservoir of drives and a GPU for frame processing, allows you to store the data from your microscopes directly onto this machine, and then push that data on to whatever your infrastructure is downstream. What this does is insulate you. It provides you with insulation from, your campus IT wants to take down half of your HPC infrastructure. Oh man, what are we going to do? Well, we can collect for about 10 days nonstop on this machine, independent of them, so we're okay. I will say that installation of a buffer system behind every detector and microscope at Scripps has led to the phenomenal figure of 0 instances of downtime more than 6 hours in the entire year of 2017 last year. So I can really speak to the power of these buffer systems and keeping your facility running and constantly churning out data. Feel free to ask questions about that later. But moving on from there, right, this gray cloud, where do we put everything? Data storage. Always prepare for the worst best case. I say the worst best case because as an information scientist, one who works with data, my worst case when I'm designing an infrastructure, right, is maximum usage. You always need to prepare for that. But your PI is always going to say that the best case because they want their microscopes running 24/7, right? So to start to address this, I actually did some math and made some calculations here to try to share this, right? I took 28 data sets that were collected in the EM facility here between 2015 and 2018. And they're plotted here as a total image footprint. So that includes the size of the raw frames, flattened images, and generated images from OceanCore 2. So everything that's generated from the microscope and associated collection computers, as compared to the highest resolution achieved. And here we can see that for a high-resolution data set, the average we see, this blue dot, is 2.6 terabytes. and that's just raw data. So that's a pretty substantial amount when you consider that you can get a data set pretty quickly. The average resolution shown here is 3.7 angstroms. Now, the variability that we see here is largely due to factors like particle density, uniformity, and just quality of images. And that's not something you can particularly control for unless you're, doing a very, concise system over and over again where you get expected results over and over again. Unless you can replicate it, you're going to have variability. So while I'm going to report averages here, you should really always kind of consider the maximum, I think. The takeaway here, though, is that more data doesn't always equal higher resolution. You can collect a small data set with a high number of particles, very dense, such as this AutoAce data that was published out of the Lander Lab here at the facility, or you can collect almost 8 terabytes of images to get a high resolution structure from this larger piezo structure that was put out of the facility. It's all going to be dependent on what you're looking at. A more meaningful metric, perhaps, to look at then is the actual cost of running. So how much data we make per day, not necessarily how much data we make per structure, but how much data actually comes out per day. And I think this is a really valuable slide here that shows that those same 28 points, the average data collection rate there was about 1 terabyte per day. And that's the time from when the microscopist sat down and started, aligning the microscope to the time they got up with their last aligned frame. So this is real data taken from, I think, all 10 users, 28 sessions, something like that. Like I said in the last slide, what we really want to think about when we're designing storage to hold all this data is that the maximum collection rate is about 2 terabytes a day. And that's what we're seeing here, of course, with the K2. I don't have figures for the K3 yet, but I'm sure that the K3 will probably double this rate, I think, in practice. But this maximum data rate of about 2 terabytes a day was achieved with the Titan Krios and the K2 Summit, with the Krios running in nanoprobe mode at full tilt imaging, a ton of images. I think it was thousands of images per day. So you should really prepare for this if you have a similar setup. A couple terabytes a day is not uncommon for raw data generation. If you were to just buy 1 petabyte of storage and just sit it next to the microscope and sit it and forget it, you'd have about 500 days of runtime on that before it just filled up, which is pretty good, but there's more that goes into that, right? There's more data than just the raw data, right? You need to factor in more factors when you're buying your storage, right, or when you're looking at storage. There's not just the raw data streaming in from the microscope. There's also the user data that's generated. And generated user data can really be a monster, right? You can have a user that generates almost nothing, or you can have users that love to duplicate and generate tons of extra data, right? So the thing to think about is what I call the dam dilemma, right? Is that you've got a reservoir, and that reservoir is your data storage. And you can let water out of the reservoir by archiving data or deleting data, but in a situation of cryo-EM, the reservoir is always going to be filling up. Between the raw data coming in and the user data being generated, I don't think that in our current workspace it's possible to actually have an equilibrium there. I haven't seen it yet. I can't wait for it to happen. So you always need to be aware of how much time you have before your reservoir overflows or your storage fills up. And you need to be ready for what to do when that happens. And you always should be planning this for your worst case of collection, your worst best case. So runway time is mentioned here. We're going to come back to that later, but first I'm going to give a little bit of information about how user data is generated, right? When I say user data, it's variable. We can look at this slide. What this slide shows is a pie chart of four users at TSRI, and these are their data fingerprints, right? I've said their data footprint before because that's just how much they use. Their fingerprint is how much they make. I can look at this, and moving forward, I kind of have a metric for seeing how my users process their data. So this user here, most of the data here of the 600 gigabytes is frames, raw frames. Those you can't really account for how big they are. They're as big as they are. They extracted micrographs, they extracted particles. This is a very particle dense, or very densely populated images. So sometimes the particles actually end up larger than the micrograph stacks because of overlap in extracted box sizes. And then this user took another 20% of data. So in this case, another 120 gigabytes just to process the data. And refinements, these are done in Reliant 2.0, do take up a significant amount of size, especially when we look at user 2 here. User 2's footprint is still 20% for their others, so their refinement files. But this is 20% of 5 terabytes. So this user generated a whole extra terabyte just in refining a structure. And while, you know, that's only 20%, 20% of a lot is still a lot. So in general, just looking at these footprints, I'm not going to really speak more on them, but I think about 25% preparation of extra data is a good average. By all means, take a more, you know, treat that as a minimum because it seems to be close to the minimum. Users can generate, I mean, the sky is the limit. If you have a couple petabytes of storage and you're not really putting pressure on your users, they will fill up your storage. This person could have used another 50%, another, you know, couple terabytes to process the data. So, you know, always be prepared for that. Always make sure that your users have room to grow. But I mean, what if you don't need to worry about your users growing? What if you have a different model? And that's where we need to start talking about, you know, what do you really need? And what storage is required really depends on your specific use case. There's two models that I really see used a lot. There's a centralized storage model where, say, a facility will get together, they get a K2 and a detector, or they get a K2 detector and a microscope, and they pipe it into a big vat of storage, right? Maybe a couple petabytes, and you know, then they all have their own computers where they do their processing on the centralized storage. Everyone gets along. Eventually, it starts to fill up, and you just have to start archiving things, as I said before. Or you've got the decentralized option here, where maybe your facility has a K2 and it's outputting data, and everyone just has their own storage. You know, no one wants to share that kind of thing. So, you know, both of these are viable options. You know, it all depends on a lot of things, right? How many users do you have? What's your uptime? What microscopes and cameras and detectors you have? And your institution factors, right? Are your groups collaborative, or are you doing separate things? Do you have separate funding? Do you have infrastructure in place already? And what are you allowed to even add to that infrastructure? So these are all things that you have to think about when you're setting up a facility, and how the data will flow around it. Because no matter how your facility works, you don't want these connections to cause you downtime. Because as a facility manager or someone who is upkeeping the microscope, you know, if this user's filled up their data and they go to collect and they can't collect because they filled up their storage, they're inevitably going to blame you. So it's great to help get all of this storage going. I'll speak to both of these setups because I think they're both equally important because, you know, it's all perspective. First, we'll talk about centralized storage though. So if you've got a centralized storage system, you really want to go with tiered solutions. So tiered storage is a pretty straightforward concept in the world of storage. I'm sure George is going to talk about later more, but you've got, you know, multiple tiers of storage. You've got performance tier storage, which is flash and scratch drives. You've got capacity tiers, so you've got a ton of spinning media. This is really where the meat of your processing is. This is where all your data lives before it goes onto scratch or flash. This is usually a large disk array. And then you've got your archive tier. You've got either, you know, you've got tape or maybe an object store or the cloud, the magical cloud. The thing to note is that when we're designing a tiered storage system, right, as you go down this pyramid, capacity increases. So these archive tier, object store, tape, cloud, I mean, depending on what service you're using, these can be near infinite. Your capacity tier is where you get to make the decision of saying, oh, hey, you know, I want a petabyte on site of spinning media. And that's a perfect equilibrium between performance and capacity. And these modern solutions have more than enough speed to accommodate cryo-EM processing routines, as I'll show you later. And then performance tier is actually something that the cost per terabyte is quite high because solid state is still, I mean, solid state is coming down, costs are coming down. But, you know, performance tier, you can consider it as, you know, SSD scratching and processing nodes, or maybe you actually can afford like an actual, flash array, that kind of thing. It's going to be very high speed, but not necessary for operation. The final big benefit to all of this is that when you have this pyramid of tiered storage running, right, you've got your Scratch, you've got all your spinning media holding all of your images for processing, and you've got your archival tiers. You have access to a new breed of software called hierarchical storage management software that allows you to really control and manipulate the data in a way that is really helpful if you're managing a facility, because you can see which users are using the most data, you can see how old the data is, you can actively move data between tiers, you can handle archival. It's really helpful, and these are things that we can talk about later as well. I'll speak quickly to decentralized solutions, right? Decentralized solutions are not impossible to do, but you have to put in some management time to make them work well. I really can't stress this enough. It's something that I've talked to a few people in the area here about, and it's something, it was a great analogy that was given to me. Don't put your $1,500 data set on a $200 external drive. Don't run down to Best Buy or whatever, buy a hard drive and put your data on it. At least buy 2 drives. You always need to incorporate fault tolerance when we're talking about data. Data loss in electron microscopy, especially if you're not done processing the data, is terrible, right? If you lose your data set, right, think about the technicians that prepped your protein, the students that designed it, the postdocs, everyone who's relying on your data or your structure. You don't want them to lose what they're doing, because that's what we're doing at the end of the day, is that we're enabling good science. We're enabling scientists to use these equipment, and if we have data loss, that's pretty much the worst case, like the actual worst case. So, no matter what you do, always have a backup copy of your data ready to go, or at least a redundant storage option. So you can use something like just a bunch of drives in ZFS. That gives you redundancy and that gives you speed, but you got to put in the time to manage it. Keep in mind that these short-term stopgaps, right? If you have a decentralized small system, you're inevitably going to be running on a shorter runway time, and you need to be really active and prepared for when that fills up, because smaller systems are going to fill up a lot faster, especially with newer hardware. The biggest thing I can't recommend enough here from this slide is that in academia we have a tendency to repurpose and rebuild. Right, and that's great. There's a lot of places where we can repurpose tech in this area, but I personally do not recommend duct taping something together to hold your precious cryo-EM data on and process it. I really recommend buying something designed and specified for this, just so that you can be sure that you don't have any data loss or slowdown. This wouldn't be a computational talk without an equation, so I made this one up, right? We've been talking about runway time for a few slides now, so I'm going to wrap up this talk about storage, talking about what runway time is, right? And runway time, in my mind, is considered as your storage total divided by the rate at which you accumulate data minus the rate at which you delete data. So how much storage you have left and how much time you have before that storage is filled, right? And outside of turning things off or on, there's not a ton you can do to change this. We can try to push the equilibrium more towards data being archived and deleted promptly, but as I said earlier, you're inevitably going to fill up your systems. So what we can do are a few things here. You can decrease your raw data impact by eliminating redundancy and archiving your data immediately. That's something like I work here to ensure active archival and make sure that things get passed around and moved where they need to be quickly and promptly. You can decrease your user data impact by encouraging responsible processing, so maybe having some protocols and use cases ready for people to read. You're going to have to manage your data and hunt down data squirrels. Users inevitably store things redundantly. You can tell them that, oh, this is backed up, but they don't believe you, and then they copy it. So then you've got terabytes and terabytes just hidden away places. You need to use your tools and make sure that you're not wasting space. You need to define use policies of your resources. Just try to standardize everything so that people know when to archive and that kind of thing. to increase our archival rate, we can define things like archival policies. So, after 2 weeks, your frames are going on cold storage, and so if you need to realign them, do it by then, that kind of thing. At Scripps, we archive our raw data immediately. We maybe need to pull out of the archive 1 in 100 data sets, so we move on from there. And we often don't look back, and just optimizing the processing pipelines to eliminate redundant data. Speaking to that, increasing your deletion rate, you can remove things like generated data, overflow data from processing, or just unused data that sits around and never is used. There's a lot of overlapping themes in what we can do here. I'd say the biggest things you can do are to make use policies and archival policies, and to just really be on top of wastage. And as long as you are proactive with these things, I think you can really get the most out of whatever storage option that you use. So the quick recap of everything in storage, right? Electron detectors produce a ton of data, and you need to make sure that you have the infrastructure planned to accommodate. Your runway time, that equation we talked about, is really important when planning for the future, right? Make sure that the reservoir you build is big enough to hold everything that you plan to collect between your funding intervals. Really is what I do. You got X amount of money coming in to buy infrastructure, and that's supposed to last you so long. So do the math, think about it. How much do you really need? And that data needs are going to be increased over time as well by new technology, more users, and more devices. Right? At any point in time, depending on your facility, someone could come in and say, oh, hey, I want to put this new detector here, or we got another microscope, or we got 20 more users, that kind of thing. You need to always be ready for that. And also, the second real takeaway here is that encouraging the best practices can help you get the most out of what you have. Don't just set it and forget it. Have someone take an active role in managing and passing through the data. Just going to briefly touch on data analysis. I don't think this is more a talk speaking to storage and the data processing and setup. I'm just going to say quickly that fast storage allows for adaptive processing options. So if you properly set up storage for your microscope and all the data coming off the microscope, that will lend itself to you doing whatever you want with processing. Here at TSRI, we have a ton of processing options. We have racks of dense CPU nodes, we have workstations, and we have racks of dense GPU nodes. And our quick storage and network infrastructure allow us to interface with all of those seamlessly. It's really great. And if you take care of this from the ground up, from network to data storage to processing, you really have fluidity moving forward in how to address the problems that arise. I've talked a lot here about a lot of infrastructure things, and I'm just going to show real quickly how we've done it here at TSRI. Everything I've said to you today was it was a trial by fire. We learned this in the Crucible. We have this is an example of our setup for our Titan Krios. This is actually what we use at TSRI in our facility here. Got the microscope and the detector spitting out raw frames to our Legend on Control PC, the microscope PC, and K2 PC. They send data downstream into our frame buffer systems where the frames are aligned with NVIDIA GPUs, obviously, and sent downstream to our grid scaler system from DDN. This is where we do the majority of our processing. This system interfaces with GPU compute and CPU compute seamlessly. We've got tons of nodes at TSRI, crunching away, constantly spitting out structures. As I said earlier in the slides when I talked about the frame buffer, one of the perks is that you can easily manage the data as it comes off the scopes. We push our raw frames directly into cold archive on tape, and then our other data goes into object stores. So this whole system here, which is the fruit of a couple of years of running the facility and designing all these little points, this is really tried and true and seems to work really well for us. I'm happy to share this slide to show you how it works. But with that, just going to acknowledge everyone who's made this possible, really. Thanks to Andrew Ward and the Ward Lab for giving me the space to do this, and for Hannah and Lauren for keeping all the other parts of the lab running. The Lander Lab for taxing my infrastructure whenever they can, and to our TSR support, JC Ducom and Lisa Dong, our HPC, our HPC department, who handle a ton of this, the actual hardware here, and Bill Anderson, who manages our microscopy facility. I'd like to thank Gatan and DDN, Jen, Corey, George, and Yvonne for giving me the platform to speak to you today, and my funding sources, without whom any of this infrastructure would be possible, the NIH and the Bill and Melinda Gates Foundation. And with that, I'd pass it to you, George.
Okay, thank you, Charlie, for that great presentation. If you could advance one slide. Yeah, I'm George Vosik, and I head up all of the life sciences efforts at DDN. And I wanted to recap a couple of points raised by Charlie and that we've seen at the dozens of cryo-EM centers that we support, and re-articulate that. I think he made a very good point about having a reliable tiered storage system to handle your valuable research data, and particularly when you have a high quality instrument, you want to have an appropriate data solution to go with it, with appropriate redundancy and backup and so on. But at the core of it is a tiered storage solution where you have performance tier, capacity tier, longer term archive. And I want to stress, and if you move one, DDN can support all of those functionalities within a single archive. So we support mixed media types. You can have flash SSD in the system, you can have fast spinning disks, you can have large capacity drives. And then as Charlie introduced, a hierarchical storage manager places the data appropriately based on policies that you'd set. So you have the performance where you need it, you have the cost effectiveness where you need it. And those policies can be as simple as or as complex as you'd like. I mean, you can have it automatically paste, for instance, raw frames into an archive tier. You can have it, keep aligned frames somewhere else. You can have it take project data that hasn't been touched in 6 months and move it down to a cooler tier to free up your performance resource. And all of that happens magically. Appropriately, it also can tier out to colder storage, tape solutions, or cloud solutions as well. Another nice feature of the system is the ability to scale any of those tiers independently. And so that lets you, as you've run the center for longer and you start to accumulate more and more old project data, you can expand that capacity archive appropriately, just by adding more drives essentially. And likewise, if you get into a situation where you need more performance, you're either adding more instruments or maybe you get a new sensor because a new one's released. We've just heard excitingly about some of what to expect for the K3. Then you can add to the performance tier. And that makes DDN a perfect fit, as we've said, across all of the needs for microscopy, for supporting one of these cryo-electron instruments. And if with that, I think you can advance once or twice more to the questions. So thank you all for your time and attention today, and we are going to answer questions. If you have any, please submit them in the panel, and we'll try to get to as many as we can in the remaining minutes in the hour. And we already have a few that have come in, so we'll go to starting to answer those, but you can continue to submit as we're answering questions. So I guess the first question for Charlie, how many people run the Scripps facility in addition to you, and what are their roles?
So on my acknowledgement slide, I reached out to JC Ducom and Lisa Dong, who are our HPC core here at Scripps. They do most of the management of the actual hardware, so servers and the software stack. Other than them, I think I'm the only other one that handles the computational side of things here. We have support staff that in the Ward Lab. Hannah works on the microscopes, and Bill here is the facility manager who actually works with the microscopes as well, keeping them running. So I'd say computationally, there's just major 3 of us working on this.
Okay. And here's a more technical question to do with the K3. So I'm not sure if it's Charlie or Corey who will respond, but what is the maximum continuous bandwidth of the K3 connection between the camera and the control computer?
I guess I should take that one. The maximum bandwidth, so the details will vary depending on how you set it up, how many frames you accumulate, if you're doing super resolution, etc. A good general rule of thumb is it's not quite 4 times the data bandwidth of a K2, which is 80 gigabits per second, or 10 gigabytes per second. So we're talking on the order of 50, between 30, 40, less than 50 gigabytes per second. But again, you know, if you accumulate more frames, you're going to be saving fewer of those along your experiment runs. But that's what the camera is capable of outputting.
Okay. Next question. This diagram seems to be for K2 cameras. What network infrastructure are you using for the higher data rate coming out of the K3?
We don't actually have a K3 at Scripps yet. I'm not actually, this might be something Corey could speak to based on installations of the K3. We currently use fiber, 10 gigabit fiber for the K2. I don't know, Corey, is that sufficient for the frame output of the K3? I know that, you know, the frame rate is reduced in the end.
Correct. So the K2 is where we first introduced 10 gig fiber connections. We've simply scaled that up. We use multiple 10 gig connections. The K3, in terms of what the PC outputs, that's one of the areas we're exploring with DDN right now to see if we want to use 10 gig fiber, do we want to use InfiniBand. So internally we use the 10 gig fiber architecture, but since we're all running through a single basically super workstation PC that controls the camera, what we output is really site specific and user dependent. If your facility uses InfiniBand, we can talk about that. If you're wired for 10 gig, we can run multiple 10 gig, you know, we can do like a quad SFP. There's multiple options at that point.
And I guess building on that comment, I would say, and this isn't just true for cryo-EM, but for other instruments we've seen, a lot of times, you know, people are building a new facility for a new instrumentation, and I would strongly encourage that, you know, if you're building a new facility, go for, you know, high performance connectivity, because even if you don't absolutely need it today, you will, you know, enjoy that performance and probably need it down the line. Obviously, it's a little bit different question if you're retrofitting an old building and it's harder to get the a data line in or something like that. So let's see. Next question. Okay. It's a fairly complicated question, but I think it'll become clear as I read it out. The default for the K2 is that the dose fractions will be saved locally on the K2 PC. Did TSRI develop their own script for moving the buffer to the buffer server? And if so, could you explain what the logic behind that script?
Yes, good question, good question. So here we collect with Leginon. All of our scopes are running through this Leginon control PC. There's actually a script included with Leginon that handles that fetching of the raw frames from the K2 PC to the frame buffer. Typically, it was run on our GPFS system here, but we run it on the frame buffer now. I think the Scripps and specifically is called raw transfer.py, but I think it's included in Legion. You just have to configure it properly with the host name of your K2 PC and set up the shares between them. That script goes out to the K2 PC, fetches the frames, renames them into Legion naming specification, and puts them here. We wrote software at Scripps, or I wrote software at Scripps that takes the images and flattened images and aligned frames and pushes them onto the GPFS as they're generated. But that can be accomplished with our syncing and things like that if you don't want to have a solution that complicated. The manual or the archival of the frames I usually handle manually just to reduce data loss. I do a data set by data set depending on the needs of what the users need. But yeah, this transfer from the K2 PC to the frame buffer is done via Legion scripting.
The next one is a bit more of a sort of science question. What's the highest resolution you achieved with your Titan setup?
Oh, okay. Specifically here, I think the highest published resolution, I'm not 100% sure. Looking at the slide that I presented, I think it's 2.6 angstroms is the highest I surveyed. I certainly could follow up on that to see what the highest resolution published structure is out of the lab or out of the facility here, but I think it's down here, this guy here. So, but I can't speak to things that aren't published that I don't know about. So.
Okay. Charlie, do you have a standalone data storage and computational facility dedicated to cryo-EM that's separate from the TSRI institutional facilities?
Yes, good question. Yes and no. So our facility has been running for years. We have multiple storage options available to us. The main storage here at TSRI is shared amongst the whole institute. That's where our images pool, everything goes there. Yes, that is shared amongst other groups, proteomics, crystallography, everyone shares that. That storage is almost always full. Andrew Ward's group, our group, we have our own storage separate from that is almost solely used for cryo-EM. And then the cryo-EM facility here also has another smaller array of nodes and storage as an overflow that we use when the main storage is filled up. It's really possible to share your space with other people, but then you just have to factor that into your runway time. And things like other groups might do kind of a crash where they run a ton of jobs, and that could really slow down what you're doing. So you don't even take that into account when you're working. That's why we put the buffer systems in place here, because with our original infrastructure, we were sharing it with every other group at TSRI. When a proteomics group starts launching their jobs, they would take the cluster, kind of hang things for a little bit while it all gets sorted out, and that would pause our collection. But the buffer systems insulate us from what other people do on our shared infrastructure.
There's more questions, I guess, about the frame buffer, but I think you've answered most of them in answering that question. Let's see.
Happy to follow up as well.
Yeah, and I guess I'll say that generally to everyone as the questions are coming in. We'll make sure to follow up with every question by email if they don't get addressed, spoken in the session here. Okay. What is the effective in your tiered system? What is the effective ratio of occupancy for the more performance tier versus the archive tier?
Another good question. Our performance tier right now is about, if I'm looking at all of my systems, because we have multiple multiple options. Performance here, I'd say, is a third of the size of our archive tier on the active storage. Keep in mind that that's just looking at these object store here. So this relationship here, this GPFS and is compared to this, I think it's about a third. Maybe it's like maybe a little more than that. Most of our archival is done on tape, and that is, I don't want to say infinite, but I don't have a hard size on that because, you know, as we fill up the tapes, we just buy more tapes. So, you know, I would say that most of the footprint of modern cryo-EM processing, so I'd say post UCSF motion correction, where the alignment and dose weighting is done in the frame alignment, most of your data footprint is cold. Your raw frames go right into your archive, right? You don't really need them anymore because you've already aligned and dose weighted. So you've already eliminated almost 75% of your footprint from active storage. So that's about where our storage sits.
Okay, and then sort of tying back to the frame buffer, and I think this is more for me maybe than you, but can DDN be the frame buffer as well as the HPC archive? So as you know, Charlie spoke in their setup, you know, they're doing the frame buffer, you know, as a buffer before transferring data over the network to the more central repository. So in the Scripps location, it makes sense to have that separate buffer, and we certainly could have a DDN solution there to act as that frame buffer, a flash solution from DDN. But in other labs, depending on their setup, if they're able to have dedicated infrastructure sort of in the cryo-EM facility, then you don't have that same network issue, and so you can have it all go directly into a DDN system. So it sort of depends on how you want to set it up, but the answer is yes, we can be that solution.
Yeah, absolutely. I just want to add to that a large reason why we buffer and why we have these extra things is because, you know, we are kind of retrofitting into buildings here. You know, our microscope facility is a quarter mile away from our compute infrastructure. So, you know, those kind of things are something to take into account when you're designing this, absolutely.
Another question, I guess, for me, is there an inherent limitation with DDN on the rate of information storage based on the network? And so DDN solutions, you know, our storage is used in some of the biggest supercomputing facilities in the world. I think our largest system is a couple of terabytes per second of bandwidth, so several orders of magnitude larger than what we're talking about here for cryo-EM. So we can certainly, even our base system, you know, is far more bandwidth than what would go over a 10 gigabit line or a 40 gigabit line. We support, as Corey mentioned earlier, InfiniBand, 100 gigabit, 25 gigabit. So any network protocol you're likely to use, we can support, and the storage solution won't be the rate limiting step for the, you know, data ingest or analysis. We have performance sufficient to do, you know, multiple ingests and the analysis that goes with it simultaneously. So it's hard to read and answer at the same time, so give me 1 second to see. Okay, is it possible or practical to use the K3 computer as the Leginon computer, or would you recommend using a separate PC?
Interesting question. I think it's technically possible. We just typically use the control PCs because it just is another layer of insulation. You know, I have a spare control PCs, so if we have a problem with collection, I can swap them out at any time. But I suppose it's technically possible to do that. I don't know if that's something Gatan recommends or not, though. But and I don't know the specifications on the K3 control PC either. I should say that. So.
Yeah, I think the clock cycles on the K3 PC, we'd originally intended to be used for, processing storage of the incoming data set. So I personally don't know that we've tested that. It's something we'd have to look into before I could give you a clear cut answer.
Yeah, it's definitely been worth trying.
Okay, and then, yeah, there's still questions coming in on sort of the specification for the frame buffer machines in terms of CPU, GPU, SSD, etc. But I think that's probably one we should answer by email with technical specs rather than trying to do it over the line.
Absolutely.
With that, we're rapidly approaching the limit of the hour. So I think I'm going to say we wrap up questions, and we will go back through the remaining questions that have been submitted and answer them all by email. Thank you all again for attending, and thank you especially Charlie for presenting everything that's going on at Scripps. We appreciate you very much giving all this information. Obviously, from the amount of questions, it's been extremely well received and an important topic for everyone these days. As we said, we'll answer the questions offline that haven't been already addressed. This webinar has been recorded and will be posted on Gatan's website, and it'll be available within the next few business days. And so both if you want to come back and review it, or if you have a colleague that didn't have a chance to see the webinar, we encourage you to check that out. So thank you all very much again, and have a good day.